Okay, this lecture I will talk about chain rule, which is very useful for calculations of derivative. Actually, chain rule says that if I have functions, let us say f from u in Rn to Rm and g is a function of fu which is in now Rm to Rk, then I can define this function h which is g compose f. This is from u to Rk. And suppose x f is differentiable at x naught in u is an open set, so okay, and g is differentiable at f of x naught which belongs to interior of fu. Interior of fu means that if I have a, so if u is open, but I do not know if u is open or not. So, interior of fu means the open part of the fu, that is interior of a set A is set of all x in A such that there exists a delta x delta depending upon x such that B x delta belongs to A. Okay. So, for derivative I need open set, I have told you in the first class, because we have add and subtract things. So, if f is differentiable at x naught in u is already open. So, any open set interior is same. G is differentiable at f x naught which is interior of fu. Then what about h? That then from the chain rule of one variable, you know h is differentiable. If everything is n, m, k is 1, then h is differentiable, and derivative of h is given by g of f x to f prime of x. Here also you are given by same thing. So, actually we want to calculate, we want to show that h is differentiable at x naught, and also want to calculate dh at x naught in terms of d f x naught and dg at f x naught. This is what we want to do. This is very useful because sometime you can, even one function you can write composition of two functions and which are easy to calculate. I will give 2-3 example in the assignment, and then you will see that how one can break one function as composition of two functions and then calculate individual derivative and then apply chain rule to get the actual derivative. Since I have very short time in the lecture, I will keep all the practice problem in assignment. Okay, let us see how it is done. Okay, so we will start with the definition again. So, I have to look at h of x naught plus h minus h of x naught, but I write it in the definition. This is g at f x naught plus h, correct. H of x naught plus h is g of f x naught plus h minus g of f x naught Okay. Let me write it is this form, G equal to G of some y plus v minus G of y, where y is f x naught and y plus v is f x naught. So, v is y plus v is f x naught plus h, y is f x naught. So, v is f x naught plus h minus f x naught. Now, I have assumed f is differentiable at x naught, correct. So, what about v? I can write v as d f x naught at h plus norm h e x naught h, where e x naught h goes to 0 as h goes to 0. This is, let us number it 1. This I have used differentiability, this I have used the first assumption, f is differentiable at x naught. Well, okay. Now, g of y plus v minus g y, y is f x naught, g is differentiable at f x naught. So, why not write f x naught plus v, f of x naught plus v minus g of f x naught. This is equal to, g is differentiable at f x naught. So, that is d g at f x naught acting at v plus norm v e f x naught v, where e f x naught h v goes to 0 as v goes to 0. Look at it, I mean, let us number it 2. I have just used so far my assumption, g is f is differentiable at x naught, that gives me 1, g is differentiable at f x naught, that gives me 2, and then I will put it together to definition of h. What is it? G f x naught plus v, g f x naught. So, that is d g f x naught at v. V is, where is v? Here. Correct. I have just put v from here 1 plus the remaining term remains same. Now, look, d f x naught is what? d g f x naught is what? According to my definition, derivative is a, so d g f x naught is this is a linear operator from R n to R k. Right? This is a and d f x naught is a linear operator from R n to R m. So, this is a composition of linear operator. So, that gives me g d g f x naught composition of d f x naught h. So, if I have operator from R n to from first Rn to Rm and then Rm to Rn, then this is an operator, linear operator from Rn to Rk. Okay, this is linear. So, linearity will play here. This is a scalar comes out. So, this is dg fx naught acting at E x naught h plus I have the remaining term V fx naught v. Look at the expression carefully. If I have done some of everything correct, I think I have done right. Now, I write it, I keep it is as it is because this is my probable candidate. Plus how do I write it? I write it in a little bit different form, so that that suits my purpose. Okay, I have written a sum of two terms. This term is okay. So, I have to take care of. So, this is these two things I have written together. So, what is this fellow? EH. Tell me what is it is, just you can calculate. EH is, well, this seems to be, this is equal to, if I want to write it in norm H form, then this will be just a minute, yeah. So, d g f x naught at E x naught h plus norm V by norm H E f x naught V, but you see this is divided by norm H, but what will, so H is non-zero, but what will happen? H is 0, this term is 0, H is 0, then norm V is 0, because V is, recall what is V is, so H is 0, V is also 0, so this is 0 if H equal to 0 and this is if H not equal to 0. Convince yourself what I have written is correct. I want to show E H goes to 0 as H goes to 0. Why so? If I achieve this, then what I have got two of the answers simultaneously. Then I will have that derivative of H, that is in this case we will have, so we will have, if I show this, first of all H is differentiable, this will imply H is differentiable and dH at x naught is dg f x naught composed with df x naught. Okay, this is the last part I have to show. Now, what was E x naught h? Recall E x naught h goes to 0 as h goes to 0. Look back at your note at definition of V, and dg f x naught is a linear operator. Any linear operator, if a vector goes to 0, then it goes to 0. So, that implies dg f x naught E x naught h this goes to 0. That I have is used that if A is a linear operator, xn sequence of vectors such that xn goes to 0, then A of xn goes to 0. Straightforward linear algebra, you have it. So, this part taken care. What about this part? Well, obviously, if V goes to 0, if H goes to 0, V goes to 0 as well, because V is again f of x naught plus H minus f x naught, f is differentiable, so continuous. So, H goes to 0, V goes to 0. So, this implies E f x naught at V, this goes to 0 because G is differentiable at, this comes from the error part of G. So, G is differentiable at f x naught, so this goes to 0. This part goes to 0, no problem, but what about this part? This something is multiplied, V goes to 0, H goes to 0. Well, here it is. So, if this norm V by norm H, so something goes to 0 and this is a scalar. If this is bounded above, this is a positive quantity, this is very bounded below by 0, bounded above, then if I multiply about something is bounded above as H goes to 0, then if I multiply with something goes to 0, that goes to 0. It is very easy to, of course, all of you can convince yourself very quickly that I have multiplied some sequence going to 0 with something bounded, then it goes to 0. So, I have to show that this is bounded above. But what is V? Again, V is f x naught plus H minus f x naught, which is d f x naught H plus norm H E x naught H. So, norm V is norm of d f x naught H plus norm H E x naught H less or equal to norm of d f x naught, norm of H, we have used it before also, plus norm of H plus norm of E x naught H. That will give us norm V, but norm H is less or equal to norm of d f x naught plus norm of E x naught H, correct. Now, this quantity goes to 0 as H goes to 0. So, it will be less than say something goes to 0 as H goes to 0. So, after certain H I can say this is less than 1. So, as H goes to 0, so as, let me write it there. So, as H goes to 0, I can say that okay, E x naught H goes to 0. So, if H is less than some delta, then okay, can choose delta. Such that if H less than delta, E x naught H norm will be less than 1 because it goes to 0. So, it will be less than any positive quantity. So, that will show norm V by norm H is less than d f x naught, norm of d f x naught plus 1 as norm of H less than delta. So, this quantity remains bounded. This is what we wanted to prove, is bounded above. So, I got this. So, hence I got, hence H is again H is differentiable at x naught, and dH x naught is equal to dG composition of these two operators. If I have composition of two linear operator and if I look at their matrix, so in matrix form Jacobian of H at x naught, this will be composition of matrix of this and this, but matrix composition is simply matrix multiplication that you know from linear algebra. So, that is JG Jacobian of G at f x naught matrix multiplication. This is a M cross K matrix, and Jacobian of f at x naught, this is a G is from M to K. So, this is K cross M matrix. What is it? G was from R M to R K. So, this is a JG x naught is a K cross M matrix, and this is F is from Rn to Rm. So, this is M cross M matrix. So, this matrix is K cross N. That is okay, because H is from Rn to Rk. Okay. That is chain rule. As I said, there is a very useful one, and you will see it in assignment that there is this helps in calculation a lot. So, basically it finishes today's lecture, but I want to leave you an exercise which is not a part of chain rule, but still you may enjoy doing it, that, and also with this curiosity what happens, because if real valued function we have seen it. So, this is not part of chain rule ends there, the proof ends there. So, you try this exercise. So, suppose I have f from Rn to R, and so is G, okay, why Rn, some open set U in Rn to R real valued, so is G from U to R, x in x naught in U, then I can define this new function Hx is equal to Fx, which is real number, into Gx. So, find out what is grad H at x naught in terms of grad f and grad g. So, this is the exercise you try to do. This is very easy, just do it from definition first, but first you must think of what is a candidate, and then it is easy. Okay. So, next class we will do mean value theorem. Thank you.